Hello everybody. Today we have a privilege of having a lecture by Professor Hyman Rubinstein of the University of Melbourne. He did his PhD at the University of California at Berkeley in 1974, and he has been a professor of mathematics at the University of Melbourne since 1982. He had a position of department head there since 1989 till 1992, and then second term from 2002 to 2004. He was president of the Australian Mathematical Society from 1992 till 1994. He was elected fellow of Australian Academy of Sciences in 2003. He chaired the National Committee for the Mathematical Sciences from 2005 to 2010. He is managing director of Mine Optima since 2011. He's inaugural fellow of American Mathematical Society since 2013. And he has published 150 papers on low-dimensional geometry and topology, minimal surfaces, shortest networks with applications to undergrad mind and machine learning. Professor Rubinstein has had 20 years of experience in mind plugging, especially access networks, but also scheduling and ventilation. And he has supervised 16 PhD students and 8 Masters by Research students. So I would like to ask you to proceed with the presentation.
Thank you very much, Vera. Okay, so thanks for coming along. I guess you were having I'm sure, quite an intense program, and so this is a sort of a lunchtime extra, as I understand. Right, so this is a talk which should have lots and lots of pictures, but because I sort of produce slides, there's lots of words on the slides, and I'm going to try and draw some pictures here, which is going to be an interesting challenge. So I guess the topic is really the revolutionary developments that have occurred in geometry and topology in recent times in dimensions 2, 3 and 4. So these are usually lumped together and called low dimensions. And 5 and higher is sort of thought of as high dimensions. So there's sort of a mathematical reason rather than a pictorial reason why we sort of think of things that way. Okay, so what I'm going to do is give you a sort of a really whirlwind tour through this and just pick out a few highlights. So you've probably heard a bit about this. So I'm going to try and be non-technical, but then I have to throw in some formal stuff, and we'll see how we go here. So this is sort of an outline of the 4 bits of the talk. So the first part, I'm going to talk about surfaces. So surfaces, great stuff. You can draw them very easily. People have been interested in surfaces since ancient times. The geometry of surfaces, obviously, we use them all the time, but it's sort of really quite remarkable that everything wasn't known about surfaces, at the time of Gauss or Euler. So once people realised how to measure geometry of surfaces, why there's such an incredibly rich theory still being developed so things haven't stopped. Surfaces are still a very, very interesting part of mathematics. So the other sort of companion thing to the study of surfaces is hyperbolic geometry. So it turns out, although of course we're very used to Euclidean geometry, spherical geometry living on the Earth's surface, hyperbolic geometry is not quite so natural, but from a mathematical viewpoint it's actually much more interesting than Euclidean or spherical geometry. So it turns out it's a very important geometry. It's the right geometry to do a lot of problems. So that leads us then to this remarkable program of Bill Thurston called Thurston's Geometrization conjecture, and then it was solved more than 10 years ago in this sort of incredibly spectacular piece of work by Perelman. So I'll just sort of talk. So what I want to do is just sort of try and tell you a little bit why, you know, what these ideas are about, you know, what's the viewpoint that is there. And then just in the last 2 minutes, I'll sort of say something about the amazing world in dimension 4. So all this stuff in dimension 3 around the Poincare conjecture and sort of generalisations of that, which is sort of Thurston's view. In dimension 4, things are somehow quite different. So the other theme here is that 2 dimensions, 3 dimensions, 4 dimensions all have their own sort of special flavour. So, but there's links between them which are extremely interesting, but they're different. And then from a sort of a general mantra is dimensions 5 and higher, everything is high dimensional, and so everything sort of works somewhat the same way. So that's the sort of philosophy of what we're going to be talking about. Okay, so to start with surfaces, so this is stuff which you probably have had some exposure to. So just to remind you about, and just to set the stage here, so we're going to think about closed surfaces, so surfaces with no boundary, compact surfaces, so just these are fundamental objects, and the simple way of thinking of the orientable case is that you start with a sphere, just a 2-dimensional sphere, and then you cut some holes in it. Okay, so we sort of remove some discs, and then we attach things which we call handles. Now, a handle is really just an annulus, but we can think of it as like a tea or coffee jug, so it's a handle in that sense. And so this is a sort of a model of a closed orientable surface. Number of handles is called the genus of the surface. So I'm assuming you're sort of very, well, reasonably familiar with these gadgets. There's a nice way of thinking of these also in terms of polygons. In this case, we can take an 8-sided polygon. Sorry about my not very good drawing here. And then we can glue these sides together. So we can glue the top together in this little pattern like this. So the arrows, we're going to glue this edge to this one, and this one to this one, and the arrows are pointing in opposite directions if you're thinking circulating around the polygon. And it turns out if you do this little gluing, you in fact form a handle. The top, you do the same thing at the bottom, and then you get the bottom handle. And this equator in the middle could be thought of as just this sort of little diagonal like that. So if we chop the octagon into 2 bits, the top bit will become the top handle, and the bottom bit will become the bottom handle. Okay, so I'm hoping that you've seen this sort of game. So this game was played probably 150 years ago. People were already very familiar with surfaces and thinking about them in this way. Now, we won't say very much about it, but there is a sort of a parallel theory of non-orientable surfaces, which are extremely useful. Particularly like non-orientable surfaces, at least it's slightly different. So the difference in the model is, again, you start off with a sphere, you cut some holes in it, as we started off before, but instead of attaching a handle like a handle of a teapot, we attach a non-orientable handle. So the version of a non-orientable handle that we take is a Möbius band. So this is a band which has got a half twist in it. So it's a one-sided gadget. Now it's a little bit, you have to use your imagination a little bit here, but because we need sort of really an extra dimension to see how to do this. But in fact, what we're going to do is take the boundary circle here and glue the Möbius band onto the boundary circle. So abstractly that works fine. The boundary of the Möbius band is a circle. This is a circle, so I can glue them together. and then I'll glue another movie span into the other hole, like that. Now what the problem is you end up with a surface which doesn't embed in R3, so you cannot draw it, the whole thing. This is in fact a Klein bottle. It's a sort of a funny way of drawing it, but you may be familiar with the fact that no closed non-orientable surfaces embed in R3. You have to embed them in four-dimensional space. But at least abstractly that's what we do, and we can similarly do it by gluing up polygons. Okay, so turns out in our sort of general exploration, it's often we want to think about surfaces with boundary, but in the way we actually do it, because we're interested in geometry, not just topology, we want to think about shapes of things, we're just going to remove points rather than cut out little holes. So we're going to puncture our surface, so we're just going to remove some points. If we like, we could open them up and make them into bigger holes. Topologically you're allowed to do that, but we'll think of them as just punctures. Yeah. Okay, so automorphisms of surfaces. So this is sort of a remarkable topic. So what we're interested in is symmetries of surfaces, okay? So the theory of surfaces, I've pretty much told you most of what you need to know about how surfaces look and how you classify them. So what we want to know is what about symmetries of them. Now you might think, well, you can see symmetry interchanging these handles, but in fact it turns out there's a huge number of symmetries of surfaces. That's just the tip of the iceberg. So what I would like to do is just very quickly tell you about this theory. So this actually was developed by a mathematician in Denmark, Nielsen, in the 1920s and 1930s. And the work that he did was not, people didn't know a lot about it. Some of it he wrote in Danish, some in German. But at any rate, Bill Thurston, who was sort of this incredible genius, just completely rediscovered and extended Nielsen's work. So it's often called Nielsen-Thurston theory, this work about automorphisms of surfaces. So what we're interested in is that we have one of these surfaces and we have a map which sends the surface to itself. And by automorphism, we mean in the sense of like an invertible linear transformation or an automorphism of a group. So it's got to preserve the structure. So in our case, topologically, what we're interested in is one-to-one and onto maps which are continuous and phi inverse is continuous. Okay, so this is what we mean by automorphism. In other words, a homeomorphism. Mapping from the surface to itself, which preserves the topological structure. Now, what do we want to know about these gadgets? So what we're interested in, this actually has got to do with dynamics or dynamical systems. We'd like to know what happens when we take powers of these automorphisms. So I don't really have time to explain why, but taking powers and thinking about what happens as n goes to infinity, thinking about the asymptotics, is very much like what you do in dynamical systems. This is an example of a discrete dynamical system. So there are lots of interesting applications of this idea. We'll see just very briefly a very beautiful example of Thurston, just to illustrate how interesting this is. Okay, but that's what we'd like to know. So we'd like to know the structure of this homeomorphism so we can say something about what happens when we take powers of it. Okay, and the other thing that we're interested in is we're allowed to move the homeomorphism by continuous deformation. That's called a homotopy. Okay, so if you have come across homotopies, you'll know what I mean. Otherwise, you can just think of just moving the images of the points continuously a little bit, deforming the map through another homeomorphism. Okay, so we don't want to just look at all homeomorphisms. There are way too many. We'd like to classify them up to continuous deformation. So let's think about the two torus. And so let's do a very quick game about the two torus. Okay, so how do we think about automorphisms there? So this is, although it's a rather special case, turns out we get a rather rich classification, which has just got to do with very elementary linear algebra. But it's already giving us the right model. Okay, so the two torus, so there's lots of different models of it. So we can think of it as the Cartesian product of a circle with itself, or we can think of it as the boundary of a donut or a bagel, depending on what you like to eat. Or a nice mathematical way of thinking about it is to take the Euclidean plane and divide it up into the square lattice. So the corners of the square lattice are the integer vectors. So we can think of this as Z2. So this is, say, the origin, and so this is, for example, 2, 2. So these are all the integer pairs, and we can think of the orbit space because we can translate, of course R2 has an additive structure, we can think of Z2 as a subgroup of ZR2, and we can take the orbit space or the cosets. So we can take R2 mod Z2, and the way we can think of that is that we can obviously translate any point back into the unit square, and then we get that the sides of the unit square are translated like that by unit translation. So you get the standard model of taking a square, identifying opposite sides and getting the two torus. Now if we want to take a punctured surface, we can remove all these integer points. So if we remove all these points and take R2 minus Z2 divided by Z2, this is the two torus with a point removed, which is the origin. And this will come up in a minute. Okay, so how do we think about automorphisms of the torus? That's a homeomorphism of the torus to itself. What turns out a very nice idea is to think of automorphisms of the plane, and in fact linear transformations. So if we take a linear transformation of the plane to itself, we want one which commutes with this addition so that it will induce an automorphism of the torus. And the easy thing to do is that we just take a matrix which has got integer entries and is invertible. So obviously we want an invertible matrix because we want it to be a homeomorphism. If it has integer entries, it'll map Z2 to Z2 and the action will commute. So in fact what we get is an induced action on the torus. So it's a really interesting game to try and visualise what these automorphisms look like. Okay, they're really quite interesting. The sort of thing that you get is, for example, what's called a Day twist, where you cut the torus along a circle and then you take a twist. You can twist as many times as you like and then join up again. So a circle going around there goes to a twisted circle like that. And this is given by a matrix which looks like this. So that's the number of twists. So this is a sort of a typical automorphism that you get. These are sort of interesting things, they're not trivial. So if I twist this way, I have a positive integer. If I twist the other way, I have a negative integer. Okay, so in fact what we end up showing by sort of fairly elementary topology is that the automorphisms of the torus up to continuous deformation are exactly these linear maps. So these are the automorphisms. Okay, so how do we classify the automorphisms? And particularly, we're thinking of dynamical systems. We want to know what happens when we iterate them. Okay, so it turns out there are three types, It's very elementary to figure this out. It's a sort of a nice exercise. So it just depends on the trace, which of course determines the eigenvalues and eigenvectors. Okay, because these guys have got determinant 1, so once you know the trace, then you know the eigenvalues. So nice exercises to show that a 2 by 2 integer matrix is periodic. In other words, a to the n is the identity for some positive or negative integer n. It's a periodic map if and only if the trace is 0, 1 or minus 1. Okay, so just to convince yourself that this sort of makes sense, if I take a matrix like this has period 4 and it has trace 0. Okay, so this is a sort of typical thing that you get. Okay, so this is a sort of a really interesting fact. The periodic guys are just those guys with small trace. If the trace is 2 or minus 2, what you get is either a fixed point or a power as a fixed point. Okay, because if we take something like this is this Dane twist. This is called a twist, the Dane twist. So this is this guy which takes circles running this way and transforms them to a circle which does this. But this circle is fixed, and this is twisted. And of course, you know, it's easy, elementary, that this guy has got an eigenvector with eigenvalue 1, that's a fixed point. That's exactly what it is. And the other case where the trace is minus 1, in that case what we have to do is square it to get a fixed point, to get rid of the minus 1. Okay, so in this case, we don't have a fixed point, we have a fixed direction which is being reflected. Okay, and so what about everything else? All the guys with trace bigger than 2, or the absolute value of the trace is bigger than 2. These are called Anosov maps. So these come up, of course, Anosov did very important work in dynamical systems. These things have got 2 real eigenvalues, just sort of elementary linear algebra. One has got absolute value bigger than 1, one absolute value less than 1, because the products are 1. And so in one direction you're expanding, and in the other direction you're contracting. So this is what an Anosov map does. Okay, so we can then think about iterates, and it's very easy to see what the iterates are doing because the eigen directions are preserved. So it's easy to figure out what the powers are doing. So this is all very elementary, but interesting. So what Thurston did, and Nielsen had already sort of partly worked this out, but Thurston put it entirely in terms of modern language using measures and foliations, as he showed that exactly the same thing works for homogeneous surfaces. So what you get is you get directions, but it's sort of a lamination, a sort of a family of curves, not a single curve, where you have contracting in that direction and then you have expanding in the other direction. And so these things are called pseudo-Anosov maps. That's the name that Thurston gave them. So this is the answer. So this is a really very important result, that if you take a surface of genus G, automorphisms are periodic. So periodic means the same as before. Reducible, this sort of means that they have essentially a fixed point. We say that actually a power fixes a curve up to deformation. So it's the same as having eigenvalue plus or minus 1 in the torus case. Sort of the analogous thing. And pseudo-Anosov means it's neither reducible or periodic, so no power fixes any curve. So it's moving things around in a complicated way. Curves are all moving. Nothing gets fixed, no power fixes anything. So the amazing thing is that nearly all automorphisms are pseudo-Anosov. So reducible and periodic or periodic as a fairly small family, reducible as larger, but these pseudo-Nosov ones, Thurston gave beautiful algorithms to construct them. So there's books on this topic. So this is sort of really interesting thing. So to sort of understand what's going on, we really now need to move into the realm of geometry. So we need to start talking about geometry. So far, this has all been about topology. So Thurston again revolutionised the field by integrating geometry and topology, in particular hyperbolic geometry. So again, I'm not assuming, so I have to say very quickly, what is hyperbolic geometry? I don't know how many of you have seen it before, but at least the foundational ideas are very straightforward. So the basic idea goes back again a long way, really, to the axioms of geometry and about parallelism. So we'll say that in a minute. But what we want to do is talk about how do you compute the length of a curve. I mean, the important thing in geometry is being able to measure things, and particularly measure lengths. So in Euclidean space, this is just sort of elementary calculus. If you want to measure the length of a differentiable or smooth curve, you take the derivative, the length of the derivative, and you integrate that, and that's the length of the curve. Okay, that's just the speed that you're going along the curve. Now, in the hyperbolic plane, things change a little bit, but not a huge amount, so it's a bit deceptive. So what we do is we take the Euclidean plane again, but we divide it into two upper half. We only take the upper half plane. Okay, so we leave out all the points below the x-axis. So this is the set of points xy, where y is positive. Okay, and so what we want to do is, if we have a curve up here, how do we work out its length? So the formula is almost exactly the same, except we divide the speed by the distance to the x-axis. So if we're at a point here, and we're going at a certain speed, so we take the speed divided by this distance. So this has the effect that as you get closer to the x-axis, you're sort of going faster. The curve is getting longer and longer. So if you've ever seen Escher pictures, Escher is a sort of wonderful artist who is very interested in hyperbolic geometry. What you get is tilings where things get smaller and smaller as they get to this boundary, because you have to expand them out by this factor of 1 over the distance. Okay, so it's actually an infinite distance from here to here. This is an infinite, the x-axis is infinitely far away. It's called the ideal boundary of the hyperbolic plane. Okay, so that's sort of what it looks like. So what we're interested in is what are the mappings which preserve all the properties of this metric. So we now can work out distance between points is given by the infimum of the curves, and there is geodesics, shortest paths joining points. So let me draw a geodesic. So if I have 2 points and I want to join them by shortest path, what I do is I form a circle which has got centre on the ideal boundary. So the circle will be perpendicular to the ideal boundary, and this thing here is the geodesic. That's the unique shortest path between 2 points in the hyperbolic plane. Now, of course, you might ask, what happens if the points are vertically above each other like that? Obviously, I can't draw a circle like that. Well, the limit, if I take a sequence of points where one of the points is converging to being just above the other one, what I'm going to do is have a sequence of circles which are getting bigger and bigger, and in the limit I'll get a vertical line. So the vertical line is then the geodesic joining the 2 points. And that's the answer. That's all the geodesics that you see. And the isometries are given by very nice transformations called Möbius transformations. So what we now do is we introduce complex numbers. So it turns out the natural way of doing measurement in the hyperbolic plane is using complex coordinates. So we now, instead of using real coordinates, we think of the point as being like this instead of being Cartesian coordinates. And so these transformations, it turns out these preserve circles. So they preserve shortest paths. So they're the right things for preserving lengths. Okay, so we get this nice group of transformations. So this is very much, if you remember the torus example, the automorphisms could all be continuously deformed matrices. Here, the automorphisms can be realised by these Möbius transformations, and these are in fact matrices as well. If you compose these things, it turns out it's the same as multiplying these 2 by 2 matrices. So in fact what we get is a group of 2 by 2 matrices where the determinant is 1 and we have to divide out by minus the identity, because if you take A is minus 1 and D is minus 1 and B and C is 0, obviously you get the identity transformation. So if I want to represent this by matrix, minus the identity is the trivial map. So I have to do this little quotient to get the right answer. So it's a very cute, again, nice exercise. If you compose these things, it's the same as multiplying these matrices. Okay, so now we're into the theory of Riemann surfaces. So a Riemann surface is a surface which locally is modelled as the geometry of the hyperbolic plane. So the way you compute lengths of curves on your surface is using that formula that I wrote down a minute ago. So the idea is you think of each little piece of the surface as an element, a little disk, which you can map into the hyperbolic plane, and that's the metric that you choose. So the other way of thinking of it, which is the same way that we thought of the 2 torus, is that we can take the hyperbolic plane and divide out by what's called a lattice. So remember we thought of the 2 torus as R2 divided by Z2. So here we were thinking of the additive structure of R2, and of course translations of R2 are Euclidean isometries. So we're dividing this out by a subgroup of Euclidean isometries of the plane. So we can do the same thing in hyperbolic geometry. We can take a subgroup gamma sitting inside here, so it's R. So it's a bunch of Möbius transformations, and it has to have some properties, which I don't want to say exactly, well, I've said it here, that it's a discrete subgroup, acts without fixed points. Okay, so that's all a bit of a mouthful. Let's see a picture rather than think about the technical details. Okay, so how do you visualise how this works? So the same way that we divide the Euclidean plane up into a lattice of squares, we can divide the hyperbolic plane up into a lattice of octagons. Okay, so how do we do that? So what I'd like to do is sort of draw an octagon in the hyperbolic plane. So this octagon, I'm going to draw it very badly. I'll just start drawing it and I won't draw the rest of it. So I'm not even sure if I have the right number of sides. But these boundary curves have to be geodesics, so therefore they have to be arcs of circles. So an edge, a straight line in our geometry is a circle. So this is what our octagon is going to look like. This is a very stylised picture because it's sort of way too difficult for me to draw it really accurately. But, you know, there are lots of books where you can see pictures of these things. And the question is, what are these angles? And, of course, what are these side lengths? So what I claim, and take too long to explain it, so I hope you'll believe me about this, is I can actually make this guy symmetric where all of these sides are equal length and all of these angles are the same. They're all the same angle. And in fact, what I can do is I can make all of these angles pi and 4, 45 degrees. So how do I know that? So here's a sort of an interesting hand-wavy proof, which is, suppose I start off with a really, really tiny octagon in the hyperbolic plane. It's really small. It's actually going to look very much like a Euclidean octagon because the sides are going to be arcs of circles which are extremely short. So it's like being on the Earth's surface. If you take a very short piece of the Earth's surface, it looks very straight. So this will look extremely straight. So the angles will all look like a symmetric Euclidean octagon, and we know what the angle there is, okay? So it's going to be a lot more than 45 degrees, whatever it is, okay? So the angle is rather big if it's Euclidean octagon. So now suppose I start blowing it up like a balloon, making it bigger and bigger. So really what I'm doing is I'm moving all these points symmetrically away from some centre point. So what happens is as the circles get bigger, the angles between them get smaller. And in fact, when this thing is infinitely big, it turns out these angles go to 0. And the reason is that if I take two straight lines, they're always perpendicular to the boundary, so therefore the angle between them has to be 0. So an infinitely large symmetric octagon has got angle 0. So between 0 and the Euclidean angle, by the intermediate value theorem, I'm going to get pi and 4. So there must be an octagon which looks like that. This is sort of a really cute argument where you don't actually have to use calculations. Now what I'm going to do is just do my gluing, which I drew on the board before, just the standard gluing up of this guy to form a genus 2 surface. Okay, so here's a genus 2 surface. That's what it looks like. Now I'm going to, all of these 8 corners are going to fit together at the vertex. When you do this gluing, all the vertices get glued together. So I'm going to have 8 corners coming together here. And because the angles are all pi and 4, the total angle will be 2 pi. And so what I'm doing is the local geometry at this vertex will be the hyperbolic plane again. I've glued 8 pieces of the hyperbolic plane together to form a total hyperbolic plane around the vertex. So the local geometry everywhere is that of the hyperbolic plane, so this is a Riemann surface. So this is a sort of a little hand-wavy proof that Riemann surfaces exist. So, okay. So it turns out, you know, there are lots of automorphisms, there are lots of Riemann surfaces, and this is called type-law theory, the theory of these guys. Okay, so I'm sort of 3/4 of the way through, and we've only done dimension 2, but there's a tremendous amount there. I mean, dimension 2 is sort of amazing. So we have 3 geometries in dimension 2. We have the round sphere, so that has spherical geometry. We have the torus, which has Euclidean geometry. So this looks like R2, S2, and we have these guys, which all look like the hyperbolic plane. So Thurston's amazing insight was this way of geometrically thinking about surfaces should work for three-dimensional spaces. So if you take any space which is locally modelled on Euclidean three-dimensional space, so a sort of three-dimensional analogue of a surface or a three-manifold, we can play the same game. Now, this wasn't unheard of before Thurston, but nobody realised the immensity of this idea. I mean, this is really a very, very amazing idea. So hyperbolic through space is very easy to work out. We just take upper half space in R3. We do the length of curves the same way. Shortest paths are circles, arcs of circles again. The automorphism group works slightly differently, but almost the same. It's sort of amazing. We get Möbius transformations, but in this case, the coefficients are complex numbers. Now you might say, well, that doesn't look right because I'm transforming a complex number to a complex number. What I want is a three-dimensional vector to a three-dimensional vector. But it turns out this is okay because if I know where the so-called ideal points or the points at infinity go, then I can work out, if I have a point up here, I can work out where it goes. So this is like, sailors taking readings of where you are. All you need to do is you just take a bunch of straight lines through this point so you know where you are. Then you transform the endpoints. They move by this Möbius transformation. So you know where this point goes. So there's a unique extension of this Möbius transformation to upper half space. So that's sort of easy to prove. What's slightly harder, but not too difficult, is the other way around. If you have an automorphism of upper half space, it extends to the boundary. And so you get one of these Möbius transformations. Okay, so that tells us that things are really very nice. There's a very strong analogy between dimensions 2 and 3. So there is a wonderful example. I'll just tell you a little bit about this, which was actually in a paper in 1933, which people had forgotten about, called the two dodecahedral spaces, written in German, by Seifert and Threffel. So they described a spherical three-manifold and a hyperbolic three-manifold and talked about how similar they were and how different they were. So what they did is they took the dodecahedron, okay, so this is this gadget with pentagonal faces. Okay, so we have the Euclidean dodecahedron that has 12 pentagonal faces, and you can work out the angle between, this is about 108 degrees or something, I forget exactly what it is, but you can do the same argument in hyperbolic space as the argument I did for the existence of Riemann surfaces. And that's actually what they do in their paper. Seifert and Threffel, they say, if I take a tiny little dodecahedron in hyperbolic space, the angles between the faces are very close to Euclidean. If I make this thing get very big, I can see what the angles are when it's infinitely big. And it turns out a very easy argument shows the infinitely big guy has got angles 60 degrees between the faces, just by symmetry. Okay? So in between the Euclidean angle and the 60-degree angle, you can get 2 pi and 5, which is 72 degrees. So again, by the intermediate value theorem, there is a hyperbolic dodecahedron which is symmetric, and the angles between all the faces are 2 pi and 5. But then what they did is they wrote down an explicit way of identifying opposite faces in a symmetric way. So this is like the two torus, where the edges form 5 cycles. So you get 5 cycles of edges. So the edges, you get 5 of them matched up. There are 30 edges, and they form lots of 5, so you get 6 edges when you glue them all up. Okay, so it's like if you take the torus, if you take the square, you have 4 edges, you identify them and you get 2 in the torus. So it's the same deal. And so the same argument then tells us that the geometry of this glued up thing is hyperbolic. So this was the first example of a closed hyperbolic 3-manifold. So this is the famous dodecahedral space of Weber and Seifert. So sort of an amazing example. So here's another example, and then in my last 5 minutes I'm going to give you sort of the punchline, which is everything then was sort of, all answers have been solved in the last decade, which is sort of really quite incredible. Okay, so here's another amazing example of Thurston, which relates back to the torus example. So suppose I take the torus and remove a point, and now multiply it by an interval. So this is cross 0, 1. Now glue the ends together by an automorphism. The automorphism I choose is the one with trace 3. It's very easy to show that there is a unique matrix of trace 3 with integer entries up to conjugation. So it's sort of essentially unique. And what Thurston proved is that this thing, this gadget, has a hyperbolic metric. It's a hyperbolic manifold. Not only that, it's a non-complement. It's a very familiar space, which has been known for hundreds of years. So if we take the 3-sphere, which is Euclidean space where we add on a point of infinity to make it compact, so this is the unit sphere in R4, we take the following very simple knot. So since I'm not a knot theorist, I always have trouble drawing this to get the crossings the right way around. It's called the figure 8 knot. So there's only one sort of simpler knot than this, which is a non-hyperbolic knot, which is the trefoil knot. So this is the second most complicated knot there is. That's an extremely simple knot. And so it's really amazing that if you take this knot and remove it from the, instead of Euclidean space, you sort of want to make it compact, so you sort of compactify it. This thing has a hyperbolic metric, and this is actually it. That's another picture of it. So absolutely amazing that this is a hyperbolic 3-manifold. So just to finish now, so Thurston did many wonderful things about hyperbolic geometry, but in particular what he conjectured, so this is his famous geometrization conjecture, he conjectured that all 3-dimensional spaces, so there's some adjectives missing here, but that's a pretty good approximation, can be divided up in a unique way. So there's a unique sort of algorithm to cut them up into finite number of pieces, and each piece has one of these special metrics. So Thurston discovered what the metrics are. There are 8 of them. One of them is the spherical geometry, that's S3. You get product geometries like the 2-sphere cross a line, so that's a sort of Euclidean multiplied by Euclid, a spherical geometry, and then you have hyperbolic geometry. So this is the geometrization conjecture, and it's very much like dimension 2 in the sense that dimension 2 we have spherical geometry, Euclidean geometry and hyperbolic geometry. We don't actually have to cut things up for surfaces in the same way as here. But it is sort of really an amazing idea, and so Thurston already, he won a Fields Medal for this piece of work, plus lots of other brilliant things, but he already had shown that in some sense most 3-manifolds satisfied geometrization, but at a certain point he got stuck, In the meantime, another genius, Richard Hamilton, introduced a sort of a heat flow method for changing geometries. So you start with a metric, you improve it by sort of using a heat equation, sort of an amazing thing. And already in 1982, Hamilton had proved that a class of three manifolds were geometric using his heat flow. And then eventually, this brilliant Russian guy, Perelman, showed that Ricci flow completes Thurston's program, so we now know that all three manifolds are geometric. So it's sort of an amazing piece of mathematics, I think really quite inspirational, that we have a complete understanding in some sense, in a sort of very high level sense, of what three-dimensional spaces look like. So I was going to say a word about four-dimensional spaces, but I think probably this is a good place to stop. I think that's probably best left for another time. Okay, so thank you. So, questions? Any questions?
Hi, thanks. I'm not sure what you mean. You probably said it, but when you say that something like conforms with this geometrization conjecture, are you claiming that it meets geometric metrics? And if you do, what do you mean by geometric metric? It's just not.
Oh, right, yeah, I sort of, rushed a little bit here. So if you think in dimension 2, I mean, we have these topological things. We have a two-sphere, but of course it could look like an ellipsoid, could look like a cube, it could have lots of different shapes. Similarly, a torus, there are lots of different shapes that we can take, but for a two-sphere, there's a canonical round metric. So what do I mean by that? Well, the key idea is that every point, a neighbourhood is isometric to a neighbourhood of any other point. So in other words, there's a transformation which preserves the geometry, which just rotates any point to any other point. So that's what a geometric metric looks like, that the local picture is identical from one picture to another, from one point to another. Similarly with the two torus, if you describe it by taking Euclidean plane modulo the ladders, every point has a neighbourhood isometric to every other point, and that is isometric to a neighbourhood in Euclidean plane. And for the Riemann surface, every point is isometric to a region in the hyperbolic plane. So it's exactly the analogous thing that the three manifold, every point has a neighbourhood isometric to a standard model. And there are 8 models. One of them's the round three-sphere, one's Euclidean three-space, one's hyperbolic three-space.
Yeah. Any other question?
So really quickly, how many of these geometricizations are there in four manifolds?
Well, that's a great question. Yeah, there is a book about the geometries of four manifolds. There's something like 20, I think. The problem, though, is it only gives a tiny little tip of an enormous iceberg, unfortunately. So the geometrization conjecture fails miserably in dimension 4. So most four manifolds don't admit nice metrics in that sense. But they're still interesting. I mean, there's a lot of work done on studying geometric four manifolds, but it's not going to give you the global picture in the same way.
Okay, can I ask a question?
Sure.
So, for the right young people here who are looking for interesting problems to solve, in this field of differential geometry, what are the interesting problems, what are the directions which are really interesting for young people who are going to PhDs to explore?
Sure. no, it's a very good question. Well, I mean, in dimension 3, I mean, one of the things which I didn't mention, which Thurston was extremely influential about using computers and software, and he was a very, very early person in this area. So he got his students to develop some amazing pieces of software for geometry. So visualising these geometric structures, you can go online and download these things for free, and it is absolutely fantastic. So you can draw a knot on the screen and the computer will build the geometric structure for you. Absolutely fantastic. So this is an area there's a lot of interest in algorithms, particularly things like computational complexity. So they're sort of now becoming interesting crossover to problems in computer science and other applications of the sort of software that Thurston students pioneered. So in dimension 3, I think that's my prejudice, is that software and algorithms and really actually doing this in a concrete way is a really interesting area. Dimension 4 is wide open. There are tons of interesting problems there. That's a very, very active, interesting area.
Thank you very much, Simon. Thank you very much for your talk. So